Okay, so we're going to look at some theory that kind of lies behind a probability here. Okay, and a lot of it you'd already be familiar with anyway, and it might just be kind of underlying. So we're just looking to make a lot of it more explicit. I have a little Venn diagram recap here, okay, that just looks at kind of where different probabilities, like the things we would describe, where those sit within a Venn diagram. So if I have two events A and B, both happening as the intersection there, B but not A, so B only would be B slash A or B less A less B on the left there, and neither happening then on the outside of kind of the set there altogether. But just re-familiarizing yourself with that idea of where would each of these sections be within a Venn diagram. Very important here. We're going to start off by looking at the addition rule and how that relates to what we call mutually exclusive events. The key word here is going to be or. Okay, when we're looking at adding probabilities, or when we're required to add probabilities, the word that we're going to see is the word or. And the probability of getting A or B, which is the same as A union B, is to add A and B and subtract the intersection. Okay, and looking at our Venn diagram, the idea there basically is that the intersection is included in both. So if we add them without accounting for that intersection, then we're doubling up. Okay, we're including something twice. Okay. If two events cannot happen at the same time, okay, if they just can't happen at the same time, then we would describe them as mutually exclusive. Okay, so mutually exclusive events are two events which just cannot happen at the same time. Okay, for example, if you're tossing a coin, heads and tails would be mutually exclusive events because they can't happen together. Okay, you can't get heads and tails. So if we have mutually exclusive events, then the difference here is going to be the probability of A and B will just be 0 because they can't happen together. So that changes our addition rule to make it that the probability of getting A or B is just the sum of A and B. Okay, and that gives us the probability of A or B. Okay, non-mutually exclusive, slightly different, then we need to include or account for that possible intersection there. So looking at an example here, first of all, cards are selected at random from a deck. Calculate the probability that a king is selected. Well, a king, there is 4 kings out of the 52 cards in the deck, which is a 1 in 13 chance. A queen or a jack, well, the probability of a queen or a jack, we ask ourselves, can that happen together? Could I get a queen that is also a jack? I cannot. So that means the probability is just probability of a queen plus the probability of a jack. The probability of getting a queen, same as a king, same with a jack. So 2 in 13. Okay. Hopefully. So 1 in 13, 1 in 13, so 2 in 13 there. Yeah, grand. Okay, let's keep going. A red card or a king. So the probability of red or a king. Well, in that case, those can happen together. Okay, they are not mutually exclusive. It is possible to get a red king, so we need to consider that option as well, the or NK, okay, where it's red and a king. Probability of being red is a half. Half the cards are red. The king, we've already said, is 1 in 13 chance or 4 in 52 chance. And then the probability of getting a red king is 2 out of 52. Okay, so let's simplify this. A half plus a third plus 1 over 13 minus 2 out of 52, which is 7 in 13 chance. So a 7 in 13 chance of getting a red card or a king. So let's look at some more practice questions here for mutually exclusive. So we're asked to describe or determine if the events are mutually exclusive and then find the probability of each. So the probability of someone passing their driving test first time is 5/6. Passing the theory test on the first attempt is 9/10. Probability of passing both first time is this. Are they mutually exclusive? No. Okay, why are they not mutually exclusive? You can pass both first time. So they can happen together. Passing one first time doesn't mean you can't pass the other one first time. Okay, so both can happen together. So the probability that you pass one on either try is the probability of passing your driving test or your theory test, is the probability that you do your driving, probability that you do your theory, but we'll subtract the probability that you do both because it's already included in both of those and we only need to include it in one. So that's 5/6 plus 9/10 minus 4/5, and that gives me an answer of 14/15 there. Okay. Find the probability of selecting an ace or a red card from a deck of cards. No, they are not mutually exclusive because there are red aces. Okay, because both can happen together, they're not mutually exclusive. So the probability that I get an ace or a red card is the probability that I get an ace plus the probability that I get a red card minus the probability that I get a card that is both. The probability of getting an ace, well, there's 4 aces, so that's a 4 in 52 chance or a 1 in 13 chance. The probability of a red card is a half, and the probability of getting both a red ace, there's only 2 of those in the deck, so 2 out of 52 or 1 in 26, and that gives me an answer of 7 out of 13. Okay, the next one, the probability of two dice being tossed and showing a sum of 6 or 9. Okay, well, let's look at this. So the probability basically of getting a 6 or a 9 as a sum, well, I could get a 6 on the dice or I could get a 9. We need to consider, can I get both? If I toss a dice, could it add up to both 6 and 9? Of course not. Okay, so these events, yes, this is mutually exclusive. Okay, because it's not possible for me to toss a dice and the sum be both 6 and 9. Okay, it's one or the other. The probability that I get a sum of 6, well, that will happen 5 times out of 36. So you're thinking about 1 and 5, 2 and 4, 3 and 3. Obviously 3 and 3 is covered on both dice, and then we have the alternative 5 and 1, 4 and 2. Probability of getting a total of 9 is 4. Okay, so 4 and 5, 3 and 6, and then 6 and 3, 5 and 4. And then we've said that they can't happen together, so it's a 9 in 36 chance, which is a quarter, which isn't bad odds. Weather forecaster states that the probability of rain is 3/5, the probability of lightning is 2/5, and the probability of both is 1/5. What is the probability of rain or lightning? Okay, so we need to have a think then, are these mutually exclusive? Can it rain and cast and have lightning? It can, so though they're not mutually exclusive. Okay, we're asked the probability of rain or lightning. And from our addition rule here, that's the probability of rain plus lightning minus both. Okay, with that kind of idea or understanding that both is included in both of the probabilities, which is why we need to subtract it here. So that's going to give me 4/5 there as my probability of getting both rain or lightning. Okay, so mutually exclusive, two events that can happen, that can't happen at the same time. If they can happen at the same time, they are not mutually exclusive, and we need to consider that probability that they do happen at the same time there. So we're going to continue onwards and look at conditional probability. So conditional probability is going to be the probability of one event happening given that another event has already happened. Okay, and we write it in this format, A given B, with the kind of line between it there. And the rule is that the probability of A given B is both happening divided by the probability that B happened. So it's basically, if B has happened, out of how many of those outcomes where B happens does A also happen? Okay, and then that's kind of the probability that A happens given that B has happened. In terms of my Venn diagrams here, we would basically be focusing solely on the circle B here and looking at how many are in the intersection. And that would be the probability of A given B, because it's only the versions of A that are in that section for B. Okay, conditional probability, as I've said here, occurs when we have, for example, successive events or questions that mention without replacement. Things like that are going to kind of spark conditional probability here. So the letters A to I are written on cards and placed in a box. A card is then drawn at random. Find the probability the card chosen contains a letter in the word chair, given that the letter is a vowel. Okay, so let's see. The probability that the letter we choose is in the word chair Okay, well, let's see. If I go with the letters A to I, A, B, C, D, E, F, G, H, I, we might as well just write them out for ourselves. Okay, the probability that the word we choose or the letter we choose out of this is in the word chair, well, the only options are C, H, I, and A. We don't have or, so there's a 4 out of 9 chance that the probability of the word we choose is in the word chair. Okay, the probability that we choose a vowel, okay, is going to be 1, 2, 3. So there's a 3 in 9 chance we choose a vowel. And the probability that we choose a vowel in chair, well, that's just A and I, so a 2 in 9 chance. We are looking for here the probability that we choose a word or letter that is in the word chair, given that it is a vowel, which is the probability that it's both over the probability that we got a vowel. So the probability of getting both a word that was in the word chair and was a vowel is 2 out of 9. The probability of getting a vowel is 3 out of 9. So there's a 2 in 3 chance that the word we pick is in the word chair and is also a vowel. Okay, and that kind of does again seem kind of logical there, because out of the vowels we've picked, only 2 are in the word chair. So that kind of does make sense there. Okay, so conditional probability of A given B is the probability of both over the probability of B. The last little bit of theory then that we have is the multiplication rule, and this comes in with independent events here. Okay, this is a rule we can kind of derive from our conditional probability rule here. Okay, so by rewriting the rule, as you can see here, we work out that the probability of getting A and B, of both happening, is the probability of A given B multiplied by the probability of B. Okay, so that's a straightforward kind of multiplication rule for us here. It's the probability of A given B multiplied by the probability of B. What we need to consider though is, will there always be a case that I'll have 2 events where the probability of one event happening given another event actually has some bearing? Okay, and what that means, or what we're looking at here, or what I'm alluding to, are independent events. So an event is considered independent, okay, and think of the meaning of the word, like kind of stands on its own, is out on its own. Considered independent when the one event happening has absolutely no impact on the other event. So thinking about here, if I'm tossing 2 coins, getting a heads on one coin has no impact whatsoever on the other coin. Okay, so they would be considered independent, standalone events where the probability of one happening given another is still just the probability that that one happens. The fact that the other event happens has no bearing. And that's, I suppose, what we're getting at here with this extra line here. The probability of A given B is just the probability of A. The probability of B given A is just the probability of B. Okay, so neither really matters there. It doesn't matter that B has happened, it doesn't matter that A has happened, it doesn't change the probability for the original event there. And that's going to slightly change our multiplication rule. And you're going to find that we're going to be looking a lot of the time for independent events. Okay, they do make things a lot easier for us if events are independent. So if events are independent, then the probability of 2 things happening, A and B, is just we multiply the 2 probabilities. If they are not independent, then rather than multiplying the 2 probabilities, we multiply the probability of A given B multiplied by the probability of B. So it's really going to depend here on whether the event is independent or is not independent. It's going to just slightly change our approach to the question here, but just making sure we remember that meaning independent events means that one does not affect the other. So looking at an example here, 2 events A and B are such that probability of A is 0.7, B is 0.5, and A intersection B is 0.3. Okay, if I was to represent that on a little bit of a Venn diagram here with A and B, you see I haven't given myself much space here to draw on the intersection. Okay, 0.3 would be here, 0.4, 0.2, which adds up to everything that we have here, and then we just need to we would check as well if there's anything else. There's a 0.1 chance maybe that we're outside all of those as well. Okay, but that's neither here nor there. We might need that for this question. Find the probability of A union B. Okay, remembering that this is OR. Okay, this is kind of the word OR here. And the probability of A union B, or A or B, is A plus B minus both. Okay, and again, we could just add it up from my Venn diagram here, but 0.7 plus 0.5 minus 0.3 gives me an answer of 0.9, or I could have read that straight from my Venn diagram. And we can see how in my Venn diagram I adjusted for the fact that the 0.3 was in each of those sets A and B. Looking at part B, the conditional probability of A given B. Okay, if I was to read this from my Venn diagram, I'm looking at 0.3 there out of maybe the 0.5 that is B, but we'll try and lay this down. A intersection B over the probability of B. Well, we know that A intersection B is 0.3, B is 0.5, so it does in fact line up with what I was saying here. We look at the section that has A and consider it out of the overall section for B here. We're asked in part C to state whether they are independent and to justify our answer. So to say they're independent, we would need the probability of A given B to be equal to the probability of A, or the probability of A and B happening is the probability of A times the probability of B. Okay. Probability of A given B we worked out as 3 over 5, which is not equal to 0.7. Probability of A and B is 0.3, which, if we do a bit of multiplication here, 0.5, 0.3 is not equal to 0.35 here. Okay, so we're ending up here that the fact that A and B are not independent. Okay, if they were independent, then the probability of one would have no bearing or impact on the other whatsoever, but in fact here it does have some bearing. Okay, let's just fly through some of these exam questions here just to kind of look at the way this theory comes up, particularly now I suppose looking at the independent and conditional idea. E is the event that it will be raining tomorrow morning. F is the event that I will wear a coat. Explain why it would not be reasonable to assume E and F are independent. Well, we can just kind of talk through this one. Independent means that one has no bearing on the other. If it rains, you're more likely to wear a coat. So if it's raining, that is going to affect whether you wear a coat or not. So it wouldn't be fair to say they're independent because clearly one will impact the other. We look at the next one, so we're just going to keep moving. Two events A and B are such that probability of A is this, A intersection B is this. Find the probability of B given A. So we would need to remember a little rule here for that. So the probability of B given A is both over A, which is a half over 3/4 here. And again, we could do that on our calculator. We don't even have to use function notation. We remember that a function just represents division. That gives me 2/3 here. Okay. Probability of A union B is 11 over 12. Investigate if they're independent. So what we know about them being independent, we can test whether A, let's go with B given A, since we know it here. We could test whether B given A is equal to the probability of B, or we can test whether the probability of both A intersection B is A times B. Okay, so let's have a look at that one here. Do we have enough information to consider this one? Well, we don't actually know what the probability of B is, which I suppose is a bit of an issue here, so we might want to work that out. The probability of A union B is the probability of A plus the probability of B minus the probability of both. That comes from our addition rule here. I can fill in a lot of this information. So A is 3/4, B is unknown, probability of A intersection B is a half, and the probability of A union B is 11 over 12. This is going to give me an answer for the probability of B of 11 over 12 minus 3/4 plus a half of 2 over 3. The probability of B is 2 over 3. The probability of B given A was 2 over 3, which is equal to 2 over 3. So that to me suggests, yeah, they are independent. A intersection B was a half. Probability of A is 3/4. Probability of B is 2/3. That is a half. So those are equal as well. So yes, they are independent. One does not impact the other. Okay, what is important to consider here is even though they're independent, they were not mutually exclusive. Okay, mutually exclusive would mean that that they cannot happen at the same time. So independent events can happen at the same time. It's just that one does not impact the other. Let's keep going here. So two events G and K are such that the probability of G is 0.56, K is 0.48, and G given K is 0.25. In the Venn diagram below, write into each of the four regions the probability that the event represented by that region occurs. Okay, so we need to fill in all of these different kind of probabilities within here. Okay, so we have the probability of G, we have the probability of K. We're not told that the events are independent or anything like that, so we'll do a little bit of working out here. G given K is both over K. I know some of these values. I know that this is 0.25. I don't know the top here. I don't know the probability of both, but I do know the probability of K is 0.48. So the probability of G intersection K is 0.25 times 0.48, which is 0.12. So I can fill that into the intersection here. That allows me then to work out some of these other probabilities. 0.44 here, because I know that these two must add up to 0.56. And then over here, 0.36, because again, I know that these two have to add up to 0.48. Okay, we also just consider then, is there anything on the outside? And we'll get a 0.08 on the outside here as the probability of neither, okay, of neither happening. We would say these events are not mutually exclusive because they can happen at the same time, okay? And that's given by the fact that there is an intersection. Mutually exclusive events would have Venn diagrams like this because, as we know, the intersection would be 0. Let's keep going here to look at some of these other, or the last few example questions here. Two independent events, okay, independent kind of bolded here, so clearly important, are represented in the Venn diagram below. The probability of F without S is 1/4, both is 1/5, and F union S complement is Y, and we're told X and Y are not 0, so they are actual values. We're asked to work out X, and we're asked to work out the value of Y. Okay. So I can work out that the probability of F altogether is 1/4 plus the 1/5 in the center here. So 1/4 plus 1/5, because that's the entire circle, 9/20. Okay, we're told they're independent events. So they're independent, which means the probability of F intersection S is equal to the probability of F times the probability of S. I know that this is 1/5. I know that this is 9/20. I don't know what this is. So probability of S is 1/5 divided by 9/20, which is going to give me 4/9. Nope. Oh, I multiplied. There we go. I knew I couldn't be far off. 4/9. Okay, as my answer here for the probability of S. Okay, so that's my overall probability of S here. So the probability of S is also X plus 1/5. Okay, so another way of representing that. And I've basically just now worked out that that should be 4/9 here. So 4/9 minus 1/5 gives me 11/45 for X. 11/45 for X there. Okay, working out Y then is just 1 minus 1/4 minus 1/5 minus 11/45 is equal to Y, which means Y is 1 minus 1/4 minus 1/5 minus 11/45, 11/36. So my two answers for X and Y here, non-zero answers, but making use of that idea or that rule, that fact that they're independent. Two events are represented in the diagram. We're given some probabilities here. Write A in terms probability of A in terms of x, and hence or otherwise find the value of x for which the events are independent. So the probability of A in terms of x is x plus 0.1. Independent means the probability of both is the probability of A times the probability of B. We know a lot of these probabilities here, so I'm basically saying 0.1 is equal to x plus 0.1 times 0.4. Okay, taking all of this as the probability of B here, 0.4. Let's keep going here. 0.1 over 0.4 is equal to x plus 0.1, which means x is a quarter minus 0.1, which will give me 3 over 20, or 0.15. Okay, so in order for those events to be independent, x must be 0.15. Okay, last little question here. C and D are two events with universal set U. We've given probability of C and D. We're asked to find the maximum value of C union D complement. So let's look at this here. So this is C, this is D. We know the probability of C and the probability of D here, and I would like to maximize this value on the outside. Okay, we know that overall these probabilities should add up to give me 1. Okay, all of our Venn diagram, if I add up all the probabilities there, I should get an answer of 1. Okay, I know that there's 0.5 for C and 0.7 for D. Okay, what I know is that there has to be some sort of overlap here, because if there was no overlap, 0.5 plus 0.7 would give me an answer of 1.2, and that's over the threshold for a probability here by 0.2. So I have to have at least 0.2 of an overlap here for this situation to work. If we want to maximize this green part, then what we want to do is we want to minimize the C and D part as far as possible. The best way to do that is to make the intersection as big as possible. If I put that 0.5 in the intersection and have the 0.2 here, then that's going to minimize C union D. Okay, that's going to leave me with 0.3 as the probability of C union D complement, which is the maximum that I could possibly get. So minimizing the actual union there will maximize the complement. Okay, it kind of makes sense. If you're looking at two options, the union and its complement, if I want to make one bigger, I must make one smaller. And the only way to make the other one as big as possible is to make the other one as small as possible. So that's not even really working with independence or anything there, really. That's actually just working with sets. But I suppose overall, the three things I would say you need to know across this section here are what it means for an event to be mutually exclusive, two events to be mutually exclusive, and that idea of the addition rule. So whether we can add events, the use of the word or there when listing the certain events, and knowing that that means addition, and how that might factor in whether we need to include A and B, or whether that'll just be 0. Looking at conditional probability and the little rule that goes with that, and being able to use that rule also. And then your multiplication rule, recognizing the word and. If we use the word and for events, that's usually going to be multiplication, and knowing when we can use the multiplication of the two events as normal, and when we need to consider the conditional probability, considering whether they're independent events or whether they are not independent events.